So very similar to what we did yesterday. We're going to start off with some basic formulas. These you do need to know. We're not going to give them to you because we think they're basic enough and easy enough to memorize. So you need to know our two formulas. So if we have exponential growth, and when you think about this from a point of view on the graph, these are graphs that look like this. So exponential growth means it starts off slow growing, but then it takes off all of a sudden. And as time progresses, the number of cases increases. And again, that's what COVID is doing right now. We're on the upper end of this curve, which we don't want to be on. But the formula for that your book uses is A of t equals A naught e to the kt. So A naught e to the kt. Okay, the little A naught, that's just a notation that we tend to use. It's used a lot in physics. Chemistry uses it also. It simply means the initial population. So the population at time 0. When we talked about money yesterday, we called that P for principal. So it's the same thing. I'm just changing the letter to fit the section. K up here is your growth rate. So it's how fast the population is growing. Yesterday we called that an interest rate because your money was growing. Today it's a growth rate for population. That's if you have a growth. But what if you have a decay? So in other words, what if your population is getting smaller? So we think about that. All we have to do to make our function decrease instead of increase is do this. So that introduces a negative on the exponent. So that would be A naught e to the negative kt. So that negative is what tells you it's a decay. A naught is still the initial population. K is, instead of a growth rate, a decay rate. So, and we use decay rates when we're talking about carbon dating, radioactive substances, things that decay or get smaller over time is where we use this. So we have an exponential growth and an exponential decay. They both look like PERT with a different letter in front, but that's why we think it's easy enough to memorize them. So, okay, so we're going to jump in and try our first example. Example 1 says the number of bacteria present in a culture at time t, which is in hours. And that's the big difference between yesterday and today. The time doesn't have to be in years. You're going to see all kinds of units of time. This time it's in hours. Obeys the law of uninhibited growth. Uninhibited means exponential. This depends on the author and the problem. They'll use both. So uninhibited means exponential growth. So, and they actually give us a formula. This time they're going to call it N of t, N for number, is equal to 1,000 e to the 0.01 t. Okay, so they've already given us all of the formula, right? So again, it doesn't really matter what letters we use for the population at time t and the initial population. You can use any letters you want. Every time you switch a book, you'll see a different set of letters being used. Question A simply wants to know, determine the number of bacteria at t equal to 0. When time is 0, that means that the exponent up here is 0 and e to the 0 power is 1. So we know that the population at time 0 is going to be that beginning number of 1,000. So this just verifies where we had A naught a few minutes ago. So sure enough, your initial number of bacteria is 1,000 bacteria. Part B on that question is asking us for the growth rate. So the growth rate is K, that's our exponent up there. It's 0.01. When they're asking for it as a rate, they probably want it as a percentage. So we're going to take that 0.01 and translate it into a 1% growth rate. So there it is as a percentage. So they're just making sure you understand the vocabulary that we're using today. Part C wants to know what's the population after 4 hours. So after 4 hours, what's N of 4? So we're going to have 1,000 e to the 0.01 times 4. Okay. So if I take 0.01 times 4 as an exponent, what do we get as an answer? You guys number crunch that through for me. How many bacteria do we have?
1040.81.
Yeah, and for some reason it disturbs me to report a part of a bacteria. So, and be careful on the homework. Make sure you follow their rounding directions. We'll carry the decimals here, but watch out for what the computer program is asking you to do. But yep, so within 4 hours, we've gone from 1,000 bacteria up to 1,040 bacteria. That's quite a few. You've gained 40 bacteria in your little culture dish. So. Okay, part B says, when will the number reach 1,700? So we want to know, when is n equal to 1,700? So we're going to solve this thing for time. And this is why they're in this section. So following our formula, we're going to set the number at the end of the time as 1,700. That's going to be equal to the 1,000 e to the 0.01 t. And now we have to go solve it for t. Okay. So you're now doing the same thing we did yesterday. How do we solve this thing for t? What's my first step?
Divide 1,000.
Yep. So we're going to divide out 1,000. So 1,700 divided by 1,000 is going to be what? 17/10 or 1.7? So we'll have 1.7 equals e to the 0.01 t. And then, next step. How do we bring that exponent down?
Natural log of e.
Fantastic. Natural log of 1.7 equals the natural log of 0.01. Oops, don't do that. E to the 0.01 t. And normally I skip some steps in here, but because it's our first one for the day, we won't do that. And again, the reason we do that is that lets us bring the 0.01 t out in front. We're left with the natural log of e, and we know that that's equal to 1. So that's going to become 1. So now we just have the natural log of 1.7 equals 0.01 t. We'll divide and be done. So the natural log of 1.7 divided by 0.01 is going to give us how long it takes to reach that 1,700 mark. And what do you get?
I got 53.06.
And good. That is correct. And that will be in hours. So 53.06 hours. Wonderful. Good job. Okay, and then finally, on part E, it's asking us when will the number of bacteria double? So how long is it going to take to double? So it took 53 hours to get to 1,700. But how long is it going to take to get to doubling? Okay. So I actually want to come in and work this problem twice. You'll see why in just a second. So if I'm going to double, we start with 1,000. We know that double that population would give us 2,000. So we're going to set 2,000 equal to 1,000 e to the 0.01 t. And we'll go through the exact same process we just did. We'll divide out the 1,000. That's going to give me 2 equals e to the 0.01 t. Then in order to bring the exponent out in front, we're going to take the natural log of both sides. And we know the natural log of e is 1. We're stuck with the 0.01 t. So t is simply the natural log of 2 divided by 0.01. I do not expect it to be too much above that 53 hours. I got 69.31 hours. Because we're on the part of the curve where it's increasing sharply, so I do expect large numbers to come out even after just a few hours. So, okay, so would it really have mattered how many I started with in order to double it? Because wouldn't I always get a 2 here? So in other words, if I started with 5,000, I'd have 10,000. When I divide it out, I'd get 2. Excuse me. If I had 20 here, then I'd have 40 here. I would divide it out and get 2. So there's actually a formula that you can work through in order to do this. So if we're going to double, you're always going to have 2 equal to e to the kt. And notice what I've done is I've taken my 1 that would have been the initial population and divided it out. When you take the natural log, you're going to end up with the natural log of 2 equals k times t times the natural log of e. So the natural log of 2 is going to be equal to k times t. So if you're trying to find the growth rate, you would just divide out the time. If you're trying to find the time, you would just divide out the growth rate. So you will actually see books that have formulas for this, and it's for doubling specifically. So if we know that we're doubling, then we take the natural log of 2 divided by k to find t, or you can take the natural log of 2 and divide it by t to find k. So if you're doubling, and that's the 2. Now, if I were going to triple, I could just replace those 2's with 3's. So they're very algorithmic. In other words, in terms of what you're doing, you're going to find yourself doing the same steps over and over again with just different numbers. So it's nice to end the course in this section because of that. Okay, any comments or questions about number 1?
No.
So number 2 is a little bit more free open. They give us less information in terms of things. So the population of a Midwestern city follows the exponential law, the law of uninhibited growth. If the population went from 800,000 to 900,000 between 2003 and 2005, what will the population in 2007 be? Okay, so I'm going to write down information. So I know that in 2003, the population was 800,000. And in 2005, it's 900,000. And we want to know what's going on in 2007. Okay. So there's the information they gave me. Because it says the word exponential growth, I'm not going to go do average rate of change and things like that because it's a growth problem. So we're going to say A equals A naught e to the kt. So we're going to use the beginning info to find k. So that's my very first step. I have to find the growth rate. I need to know how fast this population is growing. So I'm going to use those first 2 pieces of information. I don't care about the time other than the fact that the time between those 2 years is a 2. So we know the population at the end of those 2 years is 900,000. It started off with 800,000 e to the k times 2. And now we're going to go solve this for k. Again, we'll do the same thing. First step, divide. So that's going to give me 900,000 over 800,000. That's just 9/8 is equal to e to the 2k. And again, I'm not going to go to a calculator on this because this is not necessarily a nice decimal. So I'm just going to leave it alone and carry it through the work. Okay, we'll come in and take the natural log. That's the natural log of 9 over 8. And that's going to be equal to 2k. I'm going to start dropping the natural log of e because at this point we know it's 1. So k is the natural log of 9 divided by 8 all over 2. And that'll give me my growth rate. So what do you guys get for k?
.058.
Yep. And I'm actually going to carry 1 more digit on that, and round that next digit to 9. So try to carry 3 numbers. I'm not going to count the 0. We won't worry about significant figures. We're just going to carry 3 actual numbers in our work. And that's mainly to get the answer that the book has or that the computer program has. You need a few digits on that, on those k's. So this is what we now know. So now we have a formula that says the population at any point in time is going to be equal to the initial 800,000 e to the 0.0589 times t. So now if you give me a year, I can tell you the population. So we've written our own formula. We wrote a function. So they want to know the population in 2007. 2007 is 4 years after 2003. And again, we're using 2003 as t equal to 0. So 2007 is t equal to 4. So we're finding a of 4. So all we have to do is put 4 in for t in our exponent and crunch it through our calculator. And that'll give us the population of the city. And what'd you get? Just read digits. That's probably the easiest way to do it.
1.012.
Yep.
Round to be 3, I guess.
Yeah. Well, so, and again, you're going to have to tell me. I don't know what that computerized homework does, right? So I've got 1012534. And the only place I'm talking about using the 3 numbers is down here on K. The rest of the time, carry all the people. They, again, may ask you to round to the nearest million. They may ask you to round to the nearest 100,000. Just depends on the problem. So, and that's in people. So in the first 2 years, we gained 100,000 people. But notice in the next 2 years, we gained from 900 to, 1,012,000. So we're gaining more in the next 2 years kind of thing. So that's an exponential growth problem. I like them. They should remind you of those variation problems because the first thing you have to do is come in and find K, which then was the constant of proportionality. So it's the same idea. You have to find K, you then write a formula, and then plug in the other information. So it's the same exact steps with a different function. Okay, so our next example, I think, is our decay example. So we can get one of those in. Yep. So example 3 says the half-life of radioactive potassium is 1.3 billion years. 1.3 billion. If 10 grams are present now, so we know that currently we have 10 grams, how much will we have in 2 million years? Big numbers. Okay. So that's just the information so that I have it. So first of all, does the term half-life make sense to you? Have you heard that term before?
Yeah.
Yeah, in chemistry maybe somewhere, right? So we know that's how long it takes for half of it to decay. So we're going to go through and use the exact same format that we did last time. We have to go find K first. So we need to find K. So we're going to start off with the fact that we have 10 grams. If we want half of it, it would be 5 grams. So again, I started off with 10 grams. I'm going down to 5 grams. Because it is getting smaller, I know I'm going to have a negative exponent. And then up there as time, I have 1.3 billion. So that's 1. That's my millions. There's my thousands, and there's the hundreds. So that's what, 1, 2, 3, 4, 5, 6, 7, 8 zeros after the 1 and the 3. That's a lot of zeros. Negative again because it's decaying. So now we're going to go solve for K. Same exact steps again. We'll divide out the 10. That's going to give me a half. Hence the term half-life. E to the negative 1, 3, 1, 2, 3, 4, 5, 6, 7, 8, K. Then we'll take the natural log of 1/2. On the right side, we'll bring the exponent out in front. And the natural log of E disappears because it's 1. And then all we have to do is divide. So the natural log of 1/2 is equal to, or divided by, it's going to be pretty tiny. Yeah, so mine went to scientific notation on this. So I have 5.33 times 10 to the negative 10th. Double check to make sure that's what you guys have got.
I got -9. But I think I forgot a zero. Doesn't add commas. Makes it hard to count.
That's why I sit here and count my zeros, right? So I know what I've got going on. So, Christina, what did you get?
I got the same thing.
Okay, so we're good then. Okay, so there's our value for K. So we now know that the amount at any given time is going to be 10e to the negative 5.33 times 10 to the negative 10th times t. So if you give me a time, I can then tell you how much we have. Well, they're telling me 2 million is our time. So when t equals 2 with 6 zeros after it, A is going to be equal to something. So now we're just plugging back in. And believe it or not, the place you're going to make mistakes on are those zeros, right? So. Fine. 2 million, 1, 2, 3, 4, 5, 6. Yeah, making sure I'm writing them right. And then times 10. Wow. So I get 9.99. It's 9.989. That's in grams. Is that what you guys are getting? See, I can't roll my zeros.
Yeah, that's what I got.
Yeah.
Good. So, and we started off with 10 grams, and after 2 million years, we still have essentially 10 grams. And that's because that 1.3 billion is so long just to get to half of it. So it does make sense that because 2 million is such a tiny part of 1.3 billion, that we haven't lost very much of it. So in terms of numbers, they're obnoxious numbers, but the problem makes sense. So. Okay, the next one we're going to do is the fossil leaf problem. Example 4. So a fossilized leaf contains 70% of its normal amount of carbon-14. So 70%, and we're dealing with carbon-14. How old is the fossil? And then they want to know, they do tell me that the half-life, so T1/2, the half-life is 5,600 years. Now, both of the problems that I picked, the half-life is in terms of years, but it could be literally in terms of minutes, it could be in terms of hours, or even days. So they're not all in terms of years. Okay, that's all they gave me. So it's the same process we just did. We have to come in and find K first. We're going to work off of the half-life problem. The difference is they don't tell me how much I have to begin with. They do tell me that at some point we have to figure out if it's 70%, if it's lost or gained. Sorry. Contains. So this is what it still has. Then they're telling me to use percentages. So instead of using grams or pounds or something like that, we're going to use percentages. So using the half-life, we got to go find K. So what we're going to do is we're going to start off with 100% of carbon-14. To do the half-life, we'll know that we'll have 50% of that. So I'm just going to use 50 and 100, and it works quite well. E to the negative K times the 5,600. Okay, I'm going to leave you guys a few minutes. Go solve for K. Tell me what K is equal to. So go do the algebra and find me a value for K. So I ended up with 1.24 times 10 to the negative fourth. Is that what you got?
Yeah, that's what I got.
Yay! Rich?
Let me see.
Okay.
1, 2, 3. Yeah.
Nicely done. Okay, now you're also going to do another carbon 14 problem. This is the value of K no matter what, so you don't have to work it through again because you've already got it. So it's up to you, but recognize that when you do it again, as long as you're using the same thing, the carbon date, still the same K. Okay, now what we're going to do is come in, and now that we know that, we can write a formula. So A equals the initial amount of 100,000, or I'm sorry, of 100%, e to the negative 1.24 times 10 to the negative 4 t. Okay, so this time, instead of giving me a time, I'm looking for the time. We've got 70% of our carbon 14. So we're going to let 70 equal 100e to the negative 1.24 times 10 to the negative 4 times t. And now we got to go solve it for t. So you do have to read these problems carefully. I keep double checking to make sure I read it correctly. So it still has 70% versus having lost 70%. So be careful with the reading, though. Okay, same process. We'll divide out the 100. That's going to give me 0.7 equals e to the negative 1.24 times 10 to the negative 4 times t. Then we'll natural log. Don't lose my negative. So t is going to be equal to whatever the natural log of 0.7 divided by that negative 1.24 times 10 to the negative 4th is equal to. So. And then what did you get?
Uh, 2876.41.
Okay.
That's the same thing.
Good job. So 28.41. Okay, so if I actually let the calculator carry all the digits on the initial one, I got 2881. So notice it's about 5 years difference. But in the course of 2,800 years, do we really care about 5 years? No. So it's all rounding. So if you're not getting the book's answer, it's because somewhere you rounded differently from what they did. But yeah, very nice job. And so do you see how repetitive the problems are? They're very repetitive. So, because you keep doing the same thing over and over again. Okay, our last example, though, is going to change things up just a little bit. So example 5 is a logistic growth problem. So what logistic growth means is it actually takes into account all the things that limit how big a population can get. So this one's all about bald eagles. So it says, suppose that 6 American bald eagles are captured and transported to Montana and set free. Based on experience, the environmentalists expect the population to grow according to the model. And this is a really ugly looking model. So 500 all over 1 plus 83.33 e to the negative 0.162t. Okay, so what this takes into account are things as oxygen. It takes into account water. It takes into account food supply. It also takes into account nesting areas, how crowded a population is, so forth. So when you graph these, and this doesn't ask us to graph them, but if you were to graph this function, it would look something like this. You'd see the beginning exponential growth, but then it starts to do this. So in other words, there's only a limit as to how much bald eagles an area can support. And so when we talk about flattening the curve with COVID, this is really what they're talking about, is limiting its factors so that it can't get any bigger. So this down here would be time, and over here would be the population. So that's what a logistic growth model does. It actually flattens out and approaches the factor. So we'll do these again in the applied calc class and talk about what this factor is up here. So that's what part A is. Part A wants to know what the carrying capacity of the environment is. So as t approaches infinity, so in other words, as the time gets bigger and bigger and bigger and bigger and bigger. So we're going to walk this through verbally versus trying to do calculus with it. So in other words, if the t over here in the exponent gets bigger and bigger and bigger, then that quantity that's sitting as an exponent gets more negative and more negative and more negative. Well, we know that that really means that it's in the denominator because of the negative exponent. So this is really becoming a really big number in the denominator of this term. So this would be 83.33 over a huge number. Well, if I take a number and divide it by a huge number, it gets smaller and smaller and smaller. So think about fractions, 1/2, 1/3, 1/4, 1/5. So as the bottom on the fraction, because the negative exponent is getting bigger, that overall term is going to 0. So what you're really left with is the 500 over the 1. So as time gets bigger and bigger and bigger, the population is going to approach that 500. So this model simply says that this area in Montana cannot support more than 500 bald eagles. That's its carrying capacity. And we got that just by talking ourselves through it. So the negative exponent means that that term is going to get tinier, which goes to 0. So you just have 500 over 1. So basically it's the top number. You have to be a little careful. If this number had been 2, I would have had to take 500 and divide it by 2. But basically anything that has the exponent with negative is going to 0. Okay, part B on that one says, what's the growth rate? It's still sitting up there on the E, so that 0.162 is our growth rate. That's a 16.2%, which is huge. That means between 1 year and the next, we've got a 16% growth. We're gaining. That's not bad at all. Part C wants to know what's the population after 3 years. So we're going to let t equal 3 and then plug it through our calculators. So P is going to be equal to the 500 all over 1 plus 83.33 e to the negative 0.162 times 3. Okay, whatever you do, make sure you put the entire denominator in a set of parentheses. And let's see if we can get it through the calculator correctly. Don't forget the negative on that exponent. So I ended up with 9.568, which we're just going to round to 10 because parts of eagles just sounds terrible. So, and is that what you got?
Yes.
Yay!
Yes.
Fantastic. Okay, part D now kind of goes not off the deep end, but gets harder all of a sudden. We now need to go solve for T. So part D is asking me, when will the population be 300 eagles? So we're going to set 300 equal to 500 all over 1 plus 83.33 e to the negative 0.162 times t. Okay, and we have to go solve this thing for time. Okay, so, well, the first thing we're going to do is clear the fraction. So what that's going to do is that's going to move the denominator from the denominator over by the 300. Is everybody comfortable with that? I multiply both sides by that common denominator. And that's going to move the denominator from the right side over to the left side. Cross multiplying would give you the same thing. Put the 300 over 1. Okay, you have a choice here. I tend to not like to distribute this 300 because it gives me a really ugly decimal sitting right here. So what I'm going to do instead is divide both sides by 300. So then I have 1 plus 83.33 e to the negative 0.162 t equals 5/3. And again, I'm not going to go to my calculator until the very end, so I'll just carry this 5/3. Okay, we're solving for t. T is trapped by the e. We have to get the e all by itself. So the first thing we're going to do is subtract that 1. So that's going to give me 83.33 e to the exponent equals what? 2/3? 5/3 minus 1, 2/3. Okay, and here's where it gets ugly for me. Our next step is to get the e by itself. We're going to divide both sides by 83.33. Luckily, we have calculators that can do wonderful things. So that's e to the negative 0.162 t equals 2/3 divided by 83.33. And that's called the complex fraction because it's a fraction within a fraction. I'm still going to leave it there. I have no idea what that is a decimal. You could probably go ahead and take it to a decimal and you'd be fine. I just don't know why I don't like to write out decimals. So now we'll natural log both sides. On the left side, the natural log of e gives me 1. So I just have the negative 0.162 t equals the natural log. And be careful, it's 2/3 divided by 83.33. Then finally, we'll divide out the decimal that's out in front. So t is going to be the natural log of 2/3 over 83.33, all divided by negative 0.162. That would be the exact answer. And that is ugly. Now I gotta go figure out what that is. Be very careful with parentheses and everything. So, natural log. So I'm going to put in another, it automatically puts this one here. I'm going to put a set of parentheses around the 2/3. So just the numerator comes out to be negative 4.82827, and then it goes on. And now I still need to divide by the negative 0.162. So I get 29.8, and I'm a little low on the board. Go over here. So it's going to take almost 30 years for the population of eagles to go from 500, I'm sorry, the 6 that we transplanted to 300. So almost 30 years. That's a long time to be tracking those 4 eagles. Okay, is that what you got?
Still typing it up.
That's okay.
Yes.
Yay! Good job. And again, it's not going to be the algebra. It's going to be the calculators that are going to be the challenge. Nicely done. Christina, is that what you got?
Yes.
Yay! Okay, Party wants to know how long does it take for the population to reach 1/2 of the carrying capacity? So what they're really asking us is if we know the carrying capacity is 500, then how long is it going to take to reach 250? So I'm going to do what I call chalkboard or whiteboard magic. I don't want to go through the whole thing again. So I'm just going to track that 250 through the work and see what happens. So that 250 would be where the 300 is, right? Then over here, this would be our 250. And 500 divided by 250 is 2. So any place I have a 5/3, I now have a 2. So this would now be 2. 2 minus 1 is now going to give me a 1. And then I can trace that all the way over to here. and that's going to be a 1. So the only difference is the 2/3 in our calculation is going to become a 1. So you can walk it through again, but recognize it's the same process. So now I'm just going to type in the 1 and see what we get for an answer. So much nicer problem. Log of 1 divided by 83.33. So very similar, right? So the numerator comes out to be negative 4.4228 divided by that negative 0.162. And that gives me 27.3. She sounds so intimidating.
Yeah.
So I get 27.3 years on mine. So not bad. I mean, we're only off by 50 from when we did the 300 eagles, right? So it makes sense that it's less time because it's a smaller population to get to. So, okay, you only have one of these on the homework because it has so many steps to it. So it's actually a shorter assignment because they're all applications. So, okay, any problems with logistic growth and decay?
No.
Okay, so the plan for next week is on Monday, I'll do a review for the exam. Tuesday, I'll hold office hours during our class time. So if you have any last minute questions, any concern about the exam, you don't have to attend unless you have a question. Wednesday, we'll do a review for the final exam, talk about the final exam. And then Thursday, I'll do office hours again. So I'll do review, office hours next week. So, and that should wrap the course up for us. Don't forget, you need to get it scheduled, and you also need to remember to send me the scratch work so I can give partial credit. So, any other comments or questions?
I'm good.
Okay, have a wonderful weekend. Enjoy it.
Too.
Maybe we'll
You
get a
too.
break.
Thank
Bye-bye.
you.